plus, and here numbers are important, rho squared over 2m. So the new coordinate we'll call rho. It's not obvious that this was the right thing to do, but it turns out that it is. Uh-oh. So what does the line element look like now? Close to r equals 2m, the line element is going to look like ds squared is equal to rho squared d of tau over, my number's right, 4m all squared plus d rho squared plus 4m squared into d theta squared plus sine squared theta d phi squared. Now, if we look at that, there are two obvious points of interest. The first is that the Euclidean horizon has become a two-sphere times something, and the two-sphere is of radius 2m and is something which you can't get rid of. What about the rho tau plane? Well, that is in fact nothing more or less than R2, although we have to be a bit careful about whether it's really R2 or whether something's funny about it. If I asked you to construct R2, metric on R2, flat metric, in polar coordinates, you would immediately say, well, rho squared d chi squared plus d rho squared is a metric on R2, but you'd have to identify chi with period 2 pi. If you didn't identify chi with period 2 pi, you'd have a real honest singularity, and the quick way to see that is to just draw a bit of R2. Let's suppose that this is rho equals 0. Rho is a distance outside here, and the meaning of moving in the chi direction is that. And so you know that if this is smooth, then the circumference of that circle has got to be equal to 2 pi, and that's why you get 2 pi identification. But suppose it wasn't. Let's suppose you started here, and you thought you were going to go round, say, to here, and then stop. So this would be trying to identify it with period less than 2 pi. You'd have to identify this surface, and that wouldn't be flat, it would be a cone with a singularity at the apex of the cone. If you calculate the scalar curvature in such a space, you will discover that the two-dimensional scalar curvature of this thing has a delta function at the origin. So that's no good. That wouldn't be a solution of the Einstein equations. It's only a solution of the Einstein equations if you identify the angle with the correct period. So what is the correct period here? You've got a factor of 4m, you've got a factor of 2 pi, and so the period is of delta tau is 1 over 8 pi m. So that's the geometry of the situation. That means that if you... Now I want this thing back. So it means that if you look at this object G, it must be periodic with period 8 pi m. This thing doesn't seem to want to behave properly today. So what does that mean physically? Well, another way of thinking about doing physics, which perhaps is less familiar unless you've done lots of condensed matter physics, is to ask yourself, what happens if you calculate a Green's function in some kind of mixed state governed by a density matrix rho? Well, the expectation value of any operator or collection of operators is going to be just trace of rho times whatever it is divided by the trace of rho. And typically you normalize your density matrices so that this thing is 1, so you don't really care about it. In the canonical ensemble, rho is just equal to e to the minus beta times the Hamiltonian, where beta is the inverse temperature. So let's consider what happens if you calculate a Green's function in such an ensemble. It's going to look something like the trace of e to the minus beta h, phi of x and t, phi of x prime and t prime. But what you can do is to remember that in the Heisenberg picture, which is the easiest thing to do, e to the iht times phi of x0, e to the minus iht is equal to phi of x and t. I hope my sign's the right way around. So this thing is really the time translation operator through a time I beta. This condition implies that g of x, x prime, t minus t prime is periodic with period I beta. So what that tells you is that if you try to look at something at non-vanishing temperature, you should expect to find the Green's functions to be periodic in imaginary time. To prove this, you just commute this thing through all the phi's and use properties of trace. This is usually called the KMS condition. Standing for Kubo Martin, and Schwinger. So that's one way of doing it, but you really want to go the other way. You want to say that if the Green's functions are periodic, that implies you have a temperature of 1 over beta. That's a more complicated calculation, but I refer you to KMS to do that. So this tells you that if you have a system in equilibrium with a black hole, it has temperature 1 over 8 pi m. So quantum field in equilibrium with a black hole has temperature 1 over beta. So from the zeroth law of thermodynamics, the black hole has that temperature. So that's how you derive the temperature of a black hole. Well, this is one way of doing it. Now, that of course has some very interesting consequences. So let's move these things out of the way. You can repeat this calculation for the Kerr-Newman sequence of metrics. It's just a bit harder and involves a grand canonical ensemble, but the ideas are basically the same. So the temperature you find is just always equal to kappa over 2 pi, where kappa is the surface gravity that we defined earlier. So that means that black holes have a temperature. Yes, you have to wait for a microphone to appear.
Hello? Test? Okay.
It's the people in the other room that will be able to hear it. You have to speak loudly so we can hear it.
Okay. So I guess this would give this calculation is done in the Hartle-Hawking vacuum, right?
Mm-hmm.
So is it a coincidence? I mean, that's not expected to be the state that arises in gravitational collapse, but is it a coincidence that you get the same temperature as you would in the Unruh vacuum, or is it?
No, it's not a coincidence, but I'm not going to try to repeat that calculation. So the comment is basically about which particular quantum state you're working in. So here we asked ourselves, what happens if the black hole is in equilibrium with its surroundings? And use the zeroth law of thermodynamics to deduce that its temperature is kappa over 2 pi. That is rather different from the original Hawking calculation, which is rather more complicated. I will say something about that calculation in a little bit. There you have to have a different vacuum state, and that vacuum state turns out to be singular on the past horizon. So it's, in terms of doing quick calculations, it's much harder. So if I put factors of h bar back in, then I would discover that the temperature was proportional to h bar. That means that the first law of black hole mechanics really is the first law of thermodynamics, provided you identify S with the area of the event horizon divided by 4. And if you do that, you'll notice that there is a factor of S will look like 1 over h bar if you put the factors of h bar back in. That tells you that the entropy is infinite classically, and that has certain interesting implications concerning the black hole information paradox. So let's ask ourselves some simple consequences of black holes having a temperature. The first is that if a black hole just sort of sits in empty space, it's going to radiate particles into empty space because it's hot. So in this kind of semi-classical picture, what you see is thermal radiation from the black hole. It will be at a temperature of kappa over 2 pi. What is the rate of that radiation? Well, the rate of energy production is just going to be the Stefan-Boltzmann factor, sigma Stefan-Boltzmann constant, times t to the 4th, then multiplied by the surface area. But that's just for one species of particle. There could be all kinds of different particles, so there'll be some kind of fudge factor depending on the nature of elementary particles. Roughly speaking, and then you sum over all of these things, and effectively alpha I is 0 for particles of mass mi less than ti, and 1 if the mass is greater than ti. But this must be equal to the rate of loss of mass, dm by dt, with a minus sign because the mass is going to decrease. Particles are being radiated, but they're not being replaced by anything. So that tells you the black hole will start to radiate away. We know what, if we just look at Schwarzschild black holes, it's easy to integrate this thing up. We're going to discover that dm dt is equal to minus some number of order 1, let's call that some constant, times t to the 4th, that's 1 over m to the 4th, and some numbers. The area is some numbers times m squared. So this is minus c times m to the minus 2. So that tells you that the black hole will evaporate away completely on a time scale of order m cubed. Now that's fine, but let's try to put this into perspective with some numbers. That's better. Thank you. Up. So just for the Schwarzschild case, let's look at some numbers. Mass, temperature, lifetime. So the obvious place, if you're an astrophysicist, to start is with the mass of the sun. 1 m sun, that's give or take 10 to the 33 grams. Temperature turns out to be 10 to the minus 7 absolute. That means it's colder than the black body background, and that therefore such black holes will actually accrete stuff from the black body background. Let's suppose that does not happen. Then its lifetime would be around 10 to the 64 years. This is the temperature of the radiation produced by a black hole of mass 1 solar mass, or 10 to the 33 grams. So that's a ridiculously long time and is clearly of no astrophysical importance. There might be smaller black holes formed in the early universe. Let's consider black holes of a mass of 10 to the 15 grams. Their temperature is approximately 10 to the 12 degrees. You might say that's rather large, but if we think of that in terms of elementary particles, this is roughly speaking the same as the mass of the pion. So in that sense, it's not completely out of our everyday experience. What's the lifetime? The answer is 1 Hubble time, more or less, 10 to the 10 years. So if you're a cosmologist, you might find this interesting. In terms of elementary particles, you might say, well, what about the Planck mass? The Planck mass is about 20 micrograms. The temperature, well, it scales like 1 over m, and this turns out to be 10 to the 32 degrees. A temperature presumed to have been attained in the early universe, but who really knows? And its lifetime will be 10 to the minus 43 seconds, 1 Planck time. It's in this region that you might hope to be able to find some direct consequences, but roughly speaking, none are known, except for what is usually called the information paradox. Let's draw a picture of what we expect from gravitational collapse and the evaporation of a black hole. So this is a Penrose diagram of such a scenario. The black hole is formed by collapsing matter, so that's going to look something like this. An event horizon is presumed to form according to the rules of cosmic censorship, or as illustrated by Oppenheimer and Snyder. So below here, it just looks like ordinary gravitational collapse. But the black hole disappears. How does it disappear? Well, you know that it's going to produce radiation out to infinity that you can see, and it's generally felt that this is a result of the pair production of particles and antiparticles that fall into the black hole as a result of being created by the strong gravitational field close to the black hole. If you had been thinking about this carefully, you would realize that there is a conflict with the second law of black hole mechanics. That said, that the change in the area between two infinitesimally related states had to be positive. But we assumed that when we derived this, I didn't derive it, but Hawking did many years ago, that the energy density of matter was positive. The energy flux crossing the horizon is negative. Otherwise, the black hole would not start to disappear. So this condition does not hold for matter crossing the horizon due to the Hawking production process. So this is not valid for the infalling radiation. This outgoing radiation is usually called Hawking radiation. And so, although on the face of it, this looks like a problem, it isn't. So we'll cross it out. There is, however, a much more serious problem. Let's consider the evolution of this system according to the rules of quantum mechanics. I could construct an initial surface down here. The black hole forms and then disappears. So a final surface sits there. If that was the case, then you'd expect that there should be a time evolution operator which goes from here to here. So we have this evolution from sigma I to sigma f, and according to the laws of quantum mechanics, the density matrix should evolve according to the von Neumann equation, rho dot is equal to h times rho, commutative with rho. Yes, that way around. That, of course, tells you that microscopic entropy is preserved. under time evolution. Von Neumann entropy, I remind you, is defined to be SEN is minus trace or rho log rho, where rho is a density matrix. Well, that's great, but doesn't seem to correspond with what we've got here. On sigma I, you could have a pure quantum state. Sigma F, well, according to this approach, sigma F consists but nothing but thermal radiation. Pure quantum states have no entropy. Thermal radiation has large entropy. And so this picture is in contradiction with the simple laws of quantum mechanics. What has gone wrong? Well, there have been many attempts at trying to understand this. One possibility, originally espoused by Hawking, is that quantum mechanics does not work. In a tease to Einstein, he said that not only does God play dice, God plays dice where he can't be seen. That is to say, inside the black hole. It could be true. You could see how it could be true, because if you... No, I want the front one to come back. Oh, no, I don't want the front one, I want this one to come back. Suppose I threw a particle into the black hole. What's going to happen? Well, according to classical physics, it will reach the singularity and fall off the edge of space-time. So that tells you that information is lost. But most of us appear to be thoroughly wedded to the idea that quantum mechanics really does work, and so something else has to be amiss. So what else could be wrong? The real problem looks as if it has to do with the entropy. The entropy of a black hole, we said, was a quarter of the area of the event horizon. If we were Boltzmann, we would say that the density of states of any system is proportional to e to the s. I should point out that this looks like, for the Schwarzschild metric, e to the 4 pi m squared. And this factor is, of course, not bounded by the Boltzmann factor. Yesterday, Veronica was busy telling us that the entropy of black holes was not extensive, and that's a reflection of that particular fact. So it looks as if we have no understanding of what these states of the black hole actually are. Do the black hole states really contain all of the information that appears in gravitational collapse or not? And the answer is simply that we do not know. There have been zillions of speculations on how this could come about, but there is no definite answer. So that is the information paradox. There seem to be roughly 16,000 citations to papers relating to this. I haven't read them all, but as I say, there is no consensus on what you're supposed to do about this. But now let's look at a slightly different calculation of the entropy. Yes. There's a race here.
So if some process purifies the final state after evolution, wouldn't that violate the second law of thermodynamics?
Not if the black hole itself was in some specific state, because its entropy would actually be zero. So the entropy that you define this way would presumably be some coarse-grained entropy. I say presumably because there is no picture of that yet. I should point out that this problem has been around for almost 50 years at this point. And so paradoxes of that type usually signal some kind of revolution in physics that has yet to occur. Now, let's suppose that we try to calculate the entropy using the methods of statistical mechanics. We would say the partition function Z at temperature T is given by some kind of path integral that looks like the integral over all metrics weighted by e to the minus action, where all metrics means all metrics periodic in imaginary time, with a period 1 over beta. Beta, not plasma. The action here is going to be the Euclidean action. But we need to be a little bit careful about this Euclidean action. At first sight, we might say, the action is equal to minus 1 over 16 pi, integral of the four-dimensional Ricci scalar. But we must ask ourselves, is that actually the variational principle we want to examine? The kind of thing that you do when you integrate over all metrics periodic in imaginary time is fix some boundary conditions at infinity. So here we want the boundary conditions at infinity, or close to infinity, to be such that there is a fixed metric on the boundary that is appropriately periodic. In other words, here is some domain. We're interested in varying G inside the action, but in such a way that the induced metric on the boundary is fixed. Now you can see that there's going to be trouble, because if I vary this, then of course the bulk term is, of course, just going to give me the Einstein equations, RAB is equal to 0. But if I vary I will discover some terms that look like suppose that G goes to GAB plus phi AB, then I'll discover terms that look like del A phi AB minus del B phi. That's the trace of this thing. And these will give me some kind of boundary terms. Those boundary terms will involve not only the induced metric on the boundary, which we'll call HAB, but will also involve the normal to the boundary. So if you think about what the induced metric is, HAB is GAB minus NANB, where N is the unit normal to the boundary. So if you fix H, but not these things, they just fly around and give you extra terms that do not allow you to have the correct variational principle. To have the correct variational principle, you need to add a boundary term. I was going to derive that, but I don't think that there is really time. The boundary term, I, turns out to be equal to minus 1 over 8 pi times the integral of the second fundamental form over the induced metric on the boundary, which is going to be delta h d3x. K is the second trace of the second fundamental form, and it's equal to the covariant derivative, well, covariant divergence of the unit normal vector. So if you add these, this term I should really call the York term. So the correct action will be I Einstein-Hilbert plus I York. Often this term is called the Gibbons-Hawking term, but in fact it was discovered by York many years earlier. If I vary this action, I will discover that the bulk term gives me RAB equals 0, and the boundary term amounts to the integral over the boundary of CAB, I'll tell you what CAB is in a moment, times KAB minus HAB times K. CAB is the projection of phi AB, the metric variation, into this boundary, into the boundary. So CAB is equal to HAC HBD phi CD. This term here is sometimes called the Brown-York stress tensor. So in some sense it represents stress tensor on the boundary, to keep the boundary in shape. That unfortunately is not all, because you have to adjust the action to be 0 in flat space time. To do that, you have to add a real Gibbons-Hawking term, I0, which is equal to plus 1 over 8 pi times the integral of K0 h to the 1/2 d3x, where this thing is evaluated in flat space with the same metric on the boundary. Let's call that just phi HAB. So what's the answer when you've done that? So what do we get? Z is equal to e to the minus 4 pi m squared into 1 plus, I guess, loop terms if you wanted to calculate them, which of course, as we all know, doesn't make a whole lot of sense. But that the partition function in the canonical ensemble is just e to the minus free energy divided by the temperature. So if you believe that, F is equal to a half m. But that's also equal to m minus Ts. So you will discover that S is equal to 4 pi m squared. This calculation can be repeated in the Kerr-Newman sequence of metrics, and in general you will end up with S is equal to a quarter A if done for Kerr-Newman. So that seems to support the Boltzmann type of interpretation of what the entropy is, but I can't tell you what the nature of the energy levels are. So what is the nature of the microstates that make up this entropy? Well, as I say, I don't know the answer to that question. There have been many suggestions, and I presume that Roberto, in his lectures, will tell you about some of the speculations that have resulted from these ideas. So thank you for listening.